Okay, we are like on time, and I will take benefit of these few minutes before our speaker or invited the speaker of today. We'll start with the webinar to introduce myself. My name is Sara Bazart. I'm glad to say that now I'm chair of the WMO San Andres Storm Warming Advisory and Assessment System Regional Steering Committee for Northern Africa, Middle East, and Europe. It's a quite long name. We have to rethink about it. And I am also part of the staff of the Barcelona Regional Center that basically is the entity that is organizing these webinars. And as you may know, we are using the Zoom webinar for these events, and you are part of the participants, then you have different options to contact us during the webinar. You have the questions and answer box on the bottom, and also the chat. Then you can write during the webinar all your questions and your comments, and then we will take care of them at the end of the event. And also remember that the webinar is recorded and is available after a few days in the website of the Barcelona Regional Center. And today with me for chairing this session on dust topics, it is Slobodan Michkovic, Carlos Perez, and Ernest Werner. All of them are connected with this WMO Regional Center hosted here in Barcelona. And I will pass the floor to Ernest, that is the technical director of the Regional Center, for introducing our speaker, or today's speaker, that I'm glad to say that is a good friend. Then I'm happy that he will accept our invitation today. And Ernest, your turn.
Thank you, Sara. Good afternoon from Barcelona. I'm going to introduce our speaker very briefly. We have today Maria González Agueitos. She's associate professor at the Technical University of Catalonia, Barcelona Tech, and collaborates as an associated researcher in the Earth Science Department of the Barcelona Supercomputing Center. Her research interests cover atmospheric aerosols and its interactions within the Earth system, with a focus on modeling the mineral dust cycle and its impact on climate. And today she will talk about mineral dust composition and how this is relevant for different aspects of the climate system, and how mineralogy can be included in models. So, okay, this is all. Maria, if you're ready, you can start.
Thank you, Ernest, and thanks, Sara, also for the introductions. I would like to thank all the organizers of this series of webinars for allowing me to present this work here. I'm very glad and happy to do so. The first thing I have to say is that what I'm going to present today is the result of a collaborative effort. So even if only my name shows in this first slide, there are many other people that have contributed to the work that I'm going to show you, both from the Barcelona Supercomputing Center, but also from other institutes. And I have to thank all of them. So I will start by something that it's, let's say, rather obvious probably for this forum, which is highlighting the importance of dust as a player in different aspects of the Earth system. We all know that dust can interact with shortwave and long-wave radiation. It can also alter cloud formation processes and act as a carrier for nutrients that, upon deposition, can have an effect on biogeochemical cycles. And also, once in the atmosphere, it reacts and interacts with different atmospheric components, and therefore has an influence also on atmospheric chemistry. Normally, we consider dust as a homogeneous bulk entity, but we know that in reality it's formed by a mixture of minerals that have different physicochemical properties. And these different minerals modulate somehow these aforementioned impacts that I was referring to. So just to mention a few more in detail, we know that, for instance, the dust absorption of radiation in the shortwave, it's somehow controlled by the amount of iron oxides and the total iron content in dust. And what you're seeing here is a series of nice plots published in a study by Di Biagio et al. Back in 2019, where they used a chamber that they have at LISA to resuspend different soil dust samples, and measure different properties, showing that the single scattering albedo in the shortwave linearly correlated for their experiments with the amount of iron oxides in their samples. Using a similar setup 2 years before, they have also identified that quartz and calcite were very relevant for the absorption of radiation in the long wave. Then, apart from the effect of minerals and radiation, we know that dust also has an impact on cloud formation processes and has been identified as a relevant ice nucleator. Several studies also in the last, let's say, 10 something years have shown that the different minerals present in dust show different efficiencies when they are acting as ice nucleators. And for instance, the study of Atkinson in 2013 that I'm showing here shows that K-feldspars are particularly effective in doing so. And also more recent study showed that quartz can also play an important role or a relevant role as an ice nucleator. Finally, I just want to mention that we know that dust that acts as a carrier for nutrients that can impact ocean and terrestrial ecosystems. And particularly for the ocean, what we are mostly interested in is in the amount of dissolved iron that is deposited over certain regions of the ocean. And we know that at emission, iron coming from dust is relatively insoluble, but its solubility increases after atmospheric processing during transport. Basically, the iron content but also somehow the ability to dissolve are linked also to the dust mineral composition. These are only a few examples of different aspects of these Earth system processes where mineralogy can be of relevance or can have an impact. However, there are still many Earth system models that consider dust as bulk homogeneous species, and that's mainly because when you have to include these new additional elements or tracers in your model, it involves normally an increase in computational time, which can be for certain types of models. For instance, these Earth system models are used normally for long-term integrations or require multiple member experiments in order to develop ensemble runs. So in this situation, increasing the computational time can be a burden, right? But apart from that, we believe that another reason for this not being widely introduced in models is because of our limited knowledge of the composition of the parent soils prone to dust emission, and also the resulting size-distributed mineralogy at emission that we have. And those are two topics that I'm going to tackle during this presentation and try to provide an overview on what we believe is the state of the art in those two aspects. And I will also show you some modeling results that compare different approaches to deal with this. So in order to have or to model dust mineralogy, we basically need these three pieces. We need to learn or know the soil mineralogical composition. From there, we need to infer the size result mineral fractions at emission, and then we are ready to trace the different minerals in our atmospheric models and resolve the atmospheric cycle of these minerals independently. If we talk about soil mineralogy, that is the databases that are available right now in order to be used in models, we have mainly two different sources of information. There are two global soil mineralogical atlases. One was developed by Klakan and his co-authors back in 1999, and also reformulated or extended by Nikovic in 2012. This map includes 8 different minerals, amongst which different clay minerals, quartz, feldspar, calcite, gypsum, and the hematite content, which is many times used as a proxy for the total iron oxides content in the soils. Then Journet and her co-authors in 2014 developed a new map, which included all those 8 minerals that were present in the previous one and added 4 additional ones. Particularly, I'm going to highlight here the different treatment of the iron oxides. So in the previous map, we considered that iron oxides or hematite was bulk entity. And here we have a distinction between the hematite and goethite fractions. Both global soil mineralogical atlases rely on the same methodology, and the base assumption or their underlying assumption is that we can take as a basis the FAO soil classification systems to infer from their soil mineralogical composition, in the sense that the classes that are defined in there are somehow linked to the physical chemical properties of the soil itself and the formation processes, and that these characteristics that are used to these FAO soil classifications are somehow inherently linked to a composition of these soils, so a mineralogy, right? So they take as a basis these FAO soil classifications, and they review the literature in order to define a mean mineralogical composition that can be assigned to each of these soil classes. What you're seeing in this small, tiny plot is a graph taken from the article of Journet, where it represents in red the points that are taken for this earlier map, let's say, and in blue the ones that were added in the more recent map developed by them. Even with a larger number of sampling points, we can see that there are some regions of the globe that still have missing data or holes in this map, right? So what these authors did was to use additional hypotheses in order to fill in the missing information. And those included empirical approaches and relating, for instance, the amount or ratios of certain minerals to information about soil texture or other data. With that, what they achieve is a mean mineralogical map that provides us with information in 2 size classes. So we have a definition of the mineralogy for the clay fraction, which is the soil sizes below 2 micrometers in diameter, and the silt sizes between 2 and 63 micrometers in diameter. I'm showing you here the mass fractions of calcites that are inferred from these 2 different maps in the clay and in the silt size classes. And you can see already at the first glance that they are slightly different. I'm going to show you or go more into the details of the differences between these 2 soil data sets, but I will do it through the results of a modeling analysis that we have done. Just to mention a few more details on the methodology they use and why these are different, I want to mention that the earlier map, that of Klakan et al. And modified by Nikovic later, it focused on the arid and semi-arid regions of the world and considered the digital soil map of the world of the FAO. They defined the mean mineralogy for 28 soil types as defined in that map. And they decided to assume that the 8 minerals they were reporting constituted the whole dust, meaning the mineral fractions are normalized and if you sum up the clay fraction or the silt fraction minerals, you will get up a 100% of the total amount, let's say. The more recent map developed by Journet and co-authors intended for a global coverage, so it extended geographically the previous map with the aim of saying, okay, if in the future or at some point I want to make an experiment or simulate dust sources that are located in different regions than in present time, maybe it will be useful to have this definition of the mineralogy at the global scale. In order to do that, they updated the FAO classification of the soil, and they used the FAO 90 and FAO 74 soil units, which increased the number of soil classes that they had to characterize with the mean mineralogy. Another difference with the Clacán soil map is that they decided to use not normalized information, or to provide non-normalized information, meaning that if you take this data set and you add up the mineral fractions that are reported for some soil units, they will amount to less than 100%. So there's a fraction that it's unknown and that we don't know which composition it has. There are other differences in between the maps, like the horizontal resolution, for instance, but I want to highlight here the different treatment of the iron oxides that I already mentioned before. And particularly, Journet distinguishes between hematite, which is assigned to the clay fraction, and goethite, which is both apportioned in the clay and the silt coarser fraction of the soil. And in the map of Journet, and originally this hematite was only apportioned in the silt, coarser size grains, but with the modification done later by Mikovic in 2012, it was also included in the clay. So what I'm showing you here in this purplish plot is not really a fair comparison, because it includes what we consider goethite in the Journet map in the silt fraction, and what it is an extension, or sorry, what it is hematite in the Clacán soil map. In any case, you can see there are large differences in this particular iron oxides fraction in between the two maps, but these are the best information we have so far to describe the parent soil's composition in our models. We know that there is a NASA mission called EMIT that will be launching an instrument to the International Space Station and will provide new information on the dust sources composition through imaging spectroscopy. So it will be very nice to see how this new data compares to our current data sets, and it will be certainly challenging also to include this new information in our models. For now, we work with the soil mineralogy that we know when we have, and what we do from there is to try to estimate the size resolved mineralogy at emission. In order to do that, we have to consider yet another issue with this information we get from these soil maps or these soil descriptions, and it's that most of the samples that are used to characterize the soil mineralogy are analyzed through wet sieving, which is a technique that is kind of destructive, and it breaks the aggregates originally present in the soil samples. The effect that actually it's important for us is that this composition that is reported in the clay fraction overemphasizes the amount of phyllosilicates compared to what would be in the original parent soil if undisturbed, right? There were several works in the past that tried to, or that corrected, proposed a method to correct this based on the breeder fragmentation theory postulated by Kopp in 2011, which allows to derive an emitted particle size distribution for dust that is independent of wind speed and other soil properties, and that can be inferred from these disturbed soil parameters. projecting these mineral fractions into the emitted particle size distribution defined by the retrofragmentation theory, what we achieve, it's a correction or a redistribution of these clay minerals into coarser grains that we will not have if we were assigning directly the soil reported fractions into our emitted minerals. So we will use this approach, this approach in our model to derive the mineral mass fractions at emission. Once we have defined how does the mineral mass fractions at emission look, we can go for the representation of the atmospheric life cycle of the minerals. And there are already a few models that consider mineralogy of dust with different complexity. I'm going to focus my talk today here in our in-house model, the atmosphere chemistry MONARCH model. But I will also show you some results briefly of these two other models listed here. The air system model is here 3 iron and the CAM model. So with MONARCH, what we have is a framework where we can actually explicitly trace the different minerals in the atmosphere, and we can use both the CLACAN dataset and the JOURNET dataset. So what we did was to conduct 3 different experiments where we used these soil maps. And in the case of JOURNET, we included the 2 versions. So one version that considers that our known minerals constitute 100% of the emitted dust, and another one that considers that there's a fraction that we don't know what it is. What you're seeing in these bar plots is the mineral mass fraction in the annual emitted budget derived from our simulation with CLACAN and our simulations with JOURNET in different regions, different source regions around the globe, and as a global average in the last bar here. What we can first say from this analysis is that both data sets have some commonalities. Both agree that clays as a sum are the more abundant minerals at emission, and they constitute approximately 40% of the total emitted dust, both in CLACAN and in JOURNET. Then the next more abundant mineral is quartz, which is a little bit higher at the global average in CLACAN, being around 40% of the total emitted dust, as compared to JOURNET, which is around 30%. And then the next more abundant mineral is feldspar, which in CLACAN it's a little bit higher in mass fraction than in JOURNET, and calcite, which is the opposite. It's a little bit higher in JOURNET than in CLACAN. If we check the different regions, we can see that there's a certain variability. And I will highlight here, for instance, the contrast between 2 important source regions, the Sahara Sahel and the North African regions, which show distinct mineralogical composition in the CLACAN dataset. And they also look different, but not exactly the same in the JOURNET dataset. I will also highlight the differences that are found in the Australian region, where the 2 datasets show quite different mass fractions at emission, and particularly we see here like a high mass fraction of kaolinite in the JOURNET dataset that is not present in this other dataset in CLACAN, sorry, which highlights or emphasizes the amount of feldspar there. There is, however, an agreement here in the fact that both datasets show that the Australian region is enriched in iron oxides there, either considered as hematite or as the sum of hematite and goethite. And then just a comment from the not normalized use of JOURNET is that this unknown composition fraction can be up to 10% of the global scale, and therefore maybe not negligible in our analysis. I will show you now basically a comparison between the CLACAN dataset and the JOURNET dataset normalized, let's say. So Just to deep a bit further in the differences at the regional level, so geographically distributed, what you're seeing here is the emitted mass fractions in the experiments conducted with Klakan mineralogy and the differences between Journet and Klakan with the same experimental setup. So just to mention that don't be scared by these hotspots here. They correspond to areas that have a low emission, and therefore they are not significant at the global scale. Our larger differences are basically over North African and Asian sources, and particularly in the Australian region, as we already saw in the maps above. What we observe when we go and check the mineral mass fractions at the surface for these minerals, quartz, feldspars, and calcite, we have on the top row the experiment with Klakan soil map, and on the bottom the differences between Journet and Klakan, is that quartz is predominant over dust sources, and particularly we see that in Journet there is a higher mass fraction of quartz all in all in the southern hemisphere, which may be related to these differences in the emitted mass fractions, both in Australian and South American sources that we observed there. There is also this hot spot here for feldspars in Klakan, which is also something that we saw in the emission budgets, and that it's not that exacerbated in the Journet data set. And finally, we see that basically a reflection of what I already said also, that in general, the Journet map presents a higher levels of calcite than the Klakan map. So another exercise that we conducted was to try to assess these modeled mineral fractions. And to do so, we used a huge data set compiled by Perwich and co-authors in 2015. What's great about their work is that they not only compile observations from the 60s to that date, but they also propose a methodology to treat somehow the heterogeneity that exists in these dust samples that are analyzed. They change in the number of minerals they report, on the size distribution, and also on the time spent in the sampling, which can be a challenge when you want to compare that to a modeled monthly mean. So we followed the same strategy as they proposed in order to compare our model results with this set of observations. I will not enter into the details here, but we can try to solve it later if it's relevant or someone is interested. So when we compare our model results with this data set, what we observe are common traits. For instance, in here you're seeing the three top panels, the Klakan mass ratios of quartz, feldspars, and calcite as simulated in surface concentration and deposition fields of our model in different size ranges. I have to say that our model on this only simulates up to 20 microns in diameter. So the colored dots are those that correspond to a modeled size distribution, and the gray dots are those that are above our modeled size range. The three upper panels show the results for Klakan and for the simulation from Klakan, and the three bottom ones show the same, but for when we use the Journet soil map. We observed that we have an overestimation of the sealed-sized bins in our model for quartz, for instance, independently of the soil map that we use. It is a little bit higher in Klakan because the quartz levels are higher there, but we attribute this to the way we have in projecting, or the method we use in projecting the size distribution at emission, and we have already a proposal in order to improve this. Then for feldspars, we observe, for instance, a lower variability in the Journet dataset as compared to the Klakan dataset used in our model, and that may be related to the fact that most of the feldspars in the silt soil fractions in your net have, let's say, been extrapolated from averaging different soil units or types, which makes this variability become lower than in the case of Klakan. Also, we see in this evaluation or in this comparison, this effect of having a higher calcite mass fractions in your net with respect to Klakans. As for the proposal to correct this emitted PSD of the mineralogy, there is a proposal by Carlos Perez and others that will somehow try to reduce this overestimation of quartz in the coarser bins. And the idea is basically to, instead of considering a bulk size distribution for the soil data, to consider a bimodal distribution in which we will take into account the clay and silt composition to define a more realistic distribution for those minerals where we have information in the two soil sizes, and then just use another mode for the phyllosilicates that are present only in the clay sizes. Sorry. So with this new strategy, the idea is to have normalized size distributions in the soil that correspond to the actual grain size distribution of the different minerals and that look more realistic, having, for instance, a size distribution for quartz and feldspars that it's more or less centered here, while you have, for instance, calcite or hematite with lower median mass diameters. So with this approach and using also the Ritter fragmentation theory, hopefully we will be able to reduce a bit this overestimation we were seeing of the quartz in the silt sizes. I am all the time reporting data and results from one model exclusively, and we wanted to look also at other models and how model variability can change how the minerals are represented in the atmosphere. And thanks to Natalie Mahoua, then Longley Lee, we had some outputs from the CAM6 models, which actually also explicitly represents different minerals in the atmosphere. And we were able to compare their model results also to the same data set. We can see that there are large differences, and we have to yet explore further which is the cause of these differences in detail. But one thing that could be behind the difference we find in our models, which, sorry, I didn't mention, Monarch is in the top row and the CAM6 results are in the bottom panels. I was saying that the differences may be attributed to the different size distribution representation. In Monarch, we use sectional representation for the different minerals that includes 8 bins, and that ranges up to 20 micrometers in diameter, while the CAM6 model uses a modal representation with 3 modes, the Aiken, accumulation, and coarse mode, to represent the different minerals, and ranges up to diameters that go up to 10 micrometers in diameter. So
10 minutes.
Okay, I will move forward. So that could be one reason behind this. Just to show you one of the minerals for which we have a larger uncertainty, which is the iron oxides. I'm showing you here again results from Monarch, and this will be the mass fraction at the surface of hematite or iron oxides represented when we use the Klakan data set. This will be the difference between the hematite itself and these mass fractions of iron oxides in Klakan. And this will be the difference when we use the hematite and goethite mass fractions in your net with respect to Klakan. Unfortunately, we don't have many observations that differentiate hematite, goethite, and iron oxides as a bulk in order to provide an estimate on which is the best representation for this mineralogy, for this mineral, sorry. But if we compare both CLACAN and UNET results with the total iron oxides observation that we have, we can see that the results are quite similar, and there's a positive effect of these larger mass fractions in the UNET dataset when we check the statistics. We have another way of assessing this, and this is work done by Vincenzo Viso and others, and it is to check how this mineralogy affects the single scattering albedo in the short wave. What you're seeing here are 4 different plots in which we consider that our monarch minerals have homogeneous composition in order to calculate the single scattering albedo, or we consider the actual different minerals that are represented both in the UNET simulation and in the CLACAN one. And this data is compared to IronNet retrievals that have been filtered to select pure dust events in a very strict way that removes other absorbing species from these dust events. What we observe is that the variability that our model predicts, it's much better when we include the mineral speciation or discrimination as compared to considering just dust as a homogeneous species in both cases. Just to conclude and show you an example of another way of using the soil mineralogy maps and representing characteristics of the dust mineralogy models, I want to show you the results that are being prepared by Elisa Bergas-Massot using ECR3 iron, which is an earth system model that incorporates a complex aqueous phase chemistry and iron dissolution representation, which now takes in consideration both calcium and iron from dust, including soil mineralogy dataset explicitly. So these 2 elements are traced along the model, and they actually, well, the calcium is used in the thermodynamic equilibrium in order to calculate, for instance, the aerosol pH. This also influences, of course, the iron solubility and the solubility rates, the soluble iron deposition in the model. With this framework, we will derive within the TOMOS project, which is an ESA project oriented to improve our knowledge on dust and ocean interactions. With this kind of model, we will develop a reconstruction of iron deposition over the ocean, and hopefully this will be used to assess also the response of the ocean biogeochemistry using the PISCES model. I just put here the Forces logo because this is another H2020 project where another version of the ECR3 is being used and further developed. And one of the objectives is to include the impact of mineralogy on cloud formation processes. And this is ongoing work also by researchers in our group in collaboration with others. So just to conclude, I'd like to highlight that mineralogy affects key aspects of our modeled dust climate interactions. We've seen at the beginning examples of its effect on radiation, nutrients, atmospheric chemistry, and potentially cloud formation. More and more, our system models account for different representations with different level of complexity of this dust mineralogy. And I would say that our current knowledge of the composition of the soils is limited, but there are some minerals for which is more robust than for others. And I will highlight clays as a bulk or quartz as more robust than for instance, calcite or feldspar amount, in which we have a larger variability among data sets, and for sure iron oxides, where we have still, I think, many uncertainties. There are also other approaches or choices that we made when we want to simulate the minerals that can affect and have an effect on the resulting mineral mass fractions that our models estimate or predict, like the way we define the emitted particle size distribution, or even the size representation of the size distribution representation in the models themselves. Something that I didn't mention is that both soil maps that we were discussing, the one from Klakan with the additions from Nikkovic and the one from Journet, have measures of uncertainty in their mineral mean mineralogical determinations, which have been barely exploited. If you want to see an example, a nice example on how this could be used in order to constrain or narrow the magnitude of the impacts of mineralogy, I would recommend you to look into this article from Longley and others in 2021. I believe that our results support that we need further observational constraints to better characterize the soil and thus the airborne dust composition, which is for which is very nice to know, for instance, that there are experimental campaigns on airborne dust characterization going on in the framework of the Fragment DRC, or that there are projects like this Emit NAS emission that are promising initiatives that will bring in more data into our modeling frameworks and possibly better data. Just want to finish highlighting that we have a framework now that allows us to assess the modeled mineralogy, including observations of mineral fractions, but also some other observations like retrievals from IronNet, and that our intention is to incorporate more models into the comparison in the future, so more model results are welcome. With this, I just thank you all for your attention, and I will be very happy to answer your questions if you have any.
Thanks a lot, Maria, for this nice talk. I think that the participants also enjoy it. We don't have anyone is writing questions. I mean, there were a question, but sorry, Osman, this is not the topic of today's webinar. And I think that someone give you a link. Then if there is time at the end of the session, we can take a look to your question about the increase of events in Sudan these days. But now is arriving one question from Pedro Julián Carrillo Pérez del Solar, that is asking I think that is a little bit also out of the scope of the topic, but it's basically asking if when are presented dust mineral models included or taken into account by international institutions when they prepare their projected hurricane track movement in the Atlantic region? I mean, sorry, Pedro, but this is not the topic of today. Today, our speaker is focusing in the how the mineralogy considered in the dust is affecting is considered in global models. Then I don't know if someone else wants to ask something specific about minerals.
I can reinterpret the question as how I interpret the question is whether models with using mineralogy are used in those projections, if they are taken into account
for climate predictions. I mean,
well, projected hurricane track. So like given that dust may be affecting hurricane formation and development.
this was a good question for one of our speakers in past month, Angela Benedetti, that was talking about seasonal predictions and including aerosols in this climate predictions exercise. I don't know, Maria, if you want to.
Yeah, I would say that not to my knowledge. I mean, I think we are still in the process of developing and introducing these mineralogical data sets within models, and then assessing them. And I don't think that there are models that consider these routinely for projections. But I'm at least I'm not aware of this. Sorry. I would say that no, but maybe there's some group that is working on that and I'm not aware of.
We have another question from Sasan, and I don't know if it's she or he, but is asking how to identify elements can help manage agricultural products in the springtime. I'm not really got the question, but Sasan, if you want, I can give you voice and then you can ask directly to Maria, because I don't know if it's because I will give you rights to talk, then everyone can listen you. Now you're mute, but if you unmute your microphone, you can ask directly to Maria your question.
Hello, Maria. Hello, Aunt Sarah. You listen me?
Yeah, we can hear you.
So good job. Thank you for this presentation. I have a question. These days, we have a dust storm in Tehran and around of the Iran. And this is the season of agriculture. And I want to know about how the identification of dust minerals and these particles help us to managing in agriculture sector. It is useful or no for us and or agriculture sector. Thank you so much.
I must admit that it is also a bit far from my expertise. Your question, sorry. I am not, let's say, an expert on agriculture management, so I cannot answer your question properly. Sorry.
If someone wants to launch directly a question to Maria, also can raise the hand. I think that, or at least to put something in the chat, and we can give you voice if typing the question in these questions and answer box is annoying you. We will wait a couple of seconds, but no, I don't think anyone writing. I have a question, because you mentioned that adding traces is something that computationally is of course costly.
Mm-hmm.
Then if you're having 8 beans in your model, considering how many, nine minerals, this is 72. How is the numbers that are associated to these simulations and also the outputs? I mean, it's something feasible, or?
Well, it is. As I said, it can be a burden for certain applications, in the sense that if you need to run long integrations and or multiple ensemble members, or if you want to go to higher resolution with this kind of models, it can be a burden to have that many different tracers, right? But I can tell you about the numbers of our own Monarch model, and I would say that adding around these 9 minerals from Clacan in a 1 degree by 1 degree simulation at the global scale, which is basically what I was showing, increases the simulation time exclusively by a 20-something% compared to not using that.
For the reason it's not in operational, right?
Well, that's one reason. Then I believe that you can always define mineralogy in your models according to the purpose that you will pursue, right? For instance, if you're maybe interested only in this biogeochemical cycles or iron, you could follow an approach such as the one followed in ECR3, which was I was mentioning just a moment ago. And in there, you account for the mineralogy of the soil and the sources of dust, but then you don't need to trace all the different mineral components. It just select, in this case, the iron content and the calcite content, for instance.
We have more questions now for you. Antonis Gikas is congratulating your talk, and he wants to ask you if you can please explain shortly what type of information we will derive from this NASA mission called EMIT.
Well, I can try. EMIT will send an instrument to the International Space Station where they will provide with, they will map with imaging spectroscopy the surface of dust sources. And these images will be then translated into mineral fractions, even with size distribution, and they will determine 10 different minerals. They are not able to infer from this technique the content of quartz and feldspars, and there they will need information coming from other data sets, but it will be, let's say, a whole new data on the surface composition, and I believe it will bring new light, particularly for the iron oxides thing, which is key.
And this we have another question from Ron Miller that is connected with about what you said now about the quartz and feldspar, and how important is this omission between given the differences between Klakan and Journet?
Yeah, that's a very good question. I think that there are larger uncertainties in the feldspar fraction than in the quartz fraction, even if they don't look much alike in the geographical distribution in between data sets. But maybe there are other ways of trying to infer this kind of quartz information. And I believe that some of the proposals were related to using also soil texture data in order to improve that. So I don't know about the direct use of these soil maps to complete the information provided by EMIT in this feldspars and quartz fraction, but maybe combining these with other information on, for instance, the soil texture as quartz increases normally with the fraction. So the coarser the grain, the higher the amount of quartz. And I think that Carlos was also exploring this kind of relationship in order to complete the missing information.
Carlos, do you want to add anything to the discussion?
What I would say is that there's sorry.
Because you were mentioned.
I think that Maria responded perfectly. So I would add only that within EMIT, there are also currently other approaches that are being explored based on other type of observations that are not basically taken into account in JURNet and CLACAN to infer quartz and feldspar in a kind of in a broad way, but still probably better than CLACAN and JURNet. And this is based on observations other than EMIT, that, you know, and will be combined. Also, there's a strategy which is to so there will be a measure. I mean, with a spectroscopy, the vegetation fraction can be discarded, so you have the remaining bare soil fraction. So one strategy of the several ones that are there is to say, okay, we have the 10 EMIT minerals, which are the major minerals over dust sources, except feldspar and quartz, and we will assume that the remaining minerals in this bare soil fraction of arid areas will be quartz and feldspar. So, which is, you know, it's a decent approximation as well. So there are several strategies there, and that will have to be tested. But for sure, EMIT as a team will also provide estimates of quartz and feldspar that are going beyond the CLACAN and JURNet.
We have a last question from Greg Schuster. Are there any long-term measurement networks that capture wind-blown dust and analyze the mineralogy? This will be helpful for linking soil mineralogy to airborne mineralogy.
Yeah, that would be great, but not to my knowledge, there are not these. So I'm not aware of any long-term measurement networks doing this.
There are campaigns that is measuring the chemical composition, but yeah, there is not regular sampling done. Cool. Greg is answered. You can use also the chat if you want for your feedback. Okay, it's 3 minutes to 4. I don't know if you have a last question for Maria. You have, like, if someone wants to say something, please put in the chat or in the questions and answer box. Otherwise, I will take benefit of this. Thanks a lot, Maria, for your time and for answering all these questions. That
Thanks to all for coming and listening and asking and everything.
If someone wants to ask directly to Maria after the webinar, we will share her email with the recorded webinar and the slides. Then I will take benefit of these minutes just to remind you that in the website of the Barcelona Dust, I don't know if you visit the new website, but all the announcements of the webinars and the news and all potential information that can be in your interest are disseminated through the newsletter that we have in the regional center. Then if you go to the home, you will see on the bottom a section where you can subscribe to the newsletter. I fully recommend that you do this action, because if there is a new webinar or a new event, you will inform through this communication channel. Also, all the news announcements and future events are in this section that you can find in the main menu. As you will see, here is the webinar of Maria, but also we are trying to pick all the events that can be in your interest. And just to remind you that in the announcement, we are including the section, but if you go to resources and you click in webinars, here you will find all the recorded webinars in addition to this is not the best example, sorry, but if we pick the one from Jasper Cox from the last month, you can see here that it's not just the recorded is also the presentation that you can download, okay? Then, unfortunately, we cannot confirm the webinar in June because we had a last minute cancellation. Then we are trying to find a good speaker for the June during the webinar, and it will be announced during the next days through the website, the mailing list, and all the communication channels that we have. Also the Twitter, remember, Barcelona_Barcelona. Then you can track all of our activities through these different dissemination channels, okay? Then with this last reminder, thanks a lot for your company today. Thanks a lot again to our speaker. It was a nice talk, Maria, and I hope to see you soon in the mid-June webinar. Bye.
Bye.